Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a thought-provoking question: the cake that is intelligence and who gets to bake it. Basically, what is true artificial general intelligence and how do we get there? It's a big question, right?
A huge question. And I think, honestly, we're closer than people realize. I mean, look at the progress in the last few years alone with deep learning. It's exponential. We're building bigger and bigger models, feeding them insane amounts of data. Eventually, something's got to give, right? Eventually, complexity will equal intelligence.
See, I really disagree with that. And I think that's kind of the crux of today's conversation, isn't it? Throwing more data at a problem, building bigger and bigger neural networks. It feels like a brute force approach that completely misses the point. It's like trying to build a skyscraper by just piling up bricks without any blueprint. You might get a tall pile of bricks, but you definitely won't get a building you can live in.
I'm somewhere in the middle, I think. I agree that brute force alone isn't the answer, but I also think that deep learning has shown us the potential. The issue, as I see it, is that current models lack a fundamental understanding of the world. They can recognize patterns, but they can't reason spatially or temporally. They don't understand cause and effect in a meaningful way.
Right, so let's break this down a bit. Otto, you're optimistic about deep learning. What specific advancements are you most excited about?
Well, look at the scaling laws, right? The bigger the model, the more data it's trained on, the better it performs. And it's not just a linear increase, it's exponential. We're seeing emergent properties that weren't explicitly programmed in. That, to me, screams intelligence. It's like the model is learning things on its own.
But what kind of learning is it? Isn't it just incredibly sophisticated pattern matching? These models are amazing at generating text that sounds human, but do they actually understand what they're saying? Can they reason about it, draw inferences, apply that knowledge to new situations in a truly intelligent way?
Well, define understand. I mean, if it can generate coherent text, answer questions, and even solve problems, isn't that a form of understanding? It might not be the same as human understanding, but who's to say ours is the only kind of intelligence? Maybe AGI will be something completely different.
That's a valid point, but I think the key difference is the ability to generalize beyond the training data. Current deep learning models are notoriously bad at that. They excel within their specific domain, but they struggle to adapt to new environments or solve problems that require a different kind of reasoning. It's like a savant who can memorize pi to 1,000,000 digits but can't figure out how to boil an egg.
Yeah, and that's where I start thinking about the brain itself. I mean, the human brain isn't just one giant neural network. It's a complex system of interconnected modules, each specialized for different tasks. There's the visual cortex, the auditory cortex, the prefrontal cortex for planning and decision-making, and they all communicate with each other. How can we replicate that kind of modularity and specialization in AI?
Exactly. And it's not just the modularity, it's the way those modules interact using symbolic representations. Think about language, for example. We don't just process raw sensory data, we represent concepts and relationships using symbols. That allows us to reason abstractly, draw inferences, and communicate complex ideas. Deep learning struggles with that kind of symbolic reasoning.
But aren't we seeing progress in that area too? I mean, look at neuro-symbolic AI. People are trying to combine the pattern recognition power of deep learning with the logical reasoning abilities of symbolic systems. It's still early days, but it's a promising direction.
It is promising, absolutely. I was just reading about a fascinating new study detailing the interplay between neuronal circuits and cognitive processes. It's showing how the brain uses both pattern recognition and symbolic manipulation. We need to figure out how to translate those biological insights into AI design principles. I think a purely algorithmic approach risks missing crucial components of biological intelligence.
And that translation is the hard part. It's easy to say we need to be more like the brain, but how do you actually do that? How do you build algorithms that capture the hierarchical structure of knowledge and allow for true reasoning and deduction?
I think part of the answer lies in understanding how the brain represents space and time. Current AI models are largely atemporal and spatial. They don't have a built-in understanding of how objects move and interact in the world. That's why they struggle with tasks like robotics or self-driving cars.
But think about the progress in reinforcement learning. We're building agents that can learn to play complex games like Go or StarCraft at a superhuman level. That requires a certain degree of spatial and temporal reasoning, doesn't it?
It does, but it's still largely based on trial and error, on learning from experience. It doesn't necessarily involve a deep understanding of the underlying physics or geometry of the game. It's more like learning a complex set of rules through repeated practice, which is different from actually understanding the game.
Exactly. It's like learning to drive by memorizing a series of actions for each situation, rather than understanding the principles of vehicle dynamics and traffic flow.
So how do we get that deeper understanding? Donald, you mentioned the importance of spatiotemporal reasoning. What specific kind of algorithms do you think we need?
I think we need algorithms that can translate between different coordinate representations. The brain is constantly transforming sensory information from one coordinate system to another. For example, converting visual information from retinal coordinates to head-centered coordinates to world-centered coordinates. Current AI models don't do that. They treat all data as being in the same abstract space, so they're missing a crucial piece of the puzzle.
That's interesting. So you're saying we need to build AI that understands geometry and physics at a fundamental level.
Exactly, and not just understands it, but can reason about it. Can make predictions about how objects will behave based on their physical properties and their interactions with the environment.
And that requires symbolic representations. You need to be able to represent concepts like gravity, momentum, and friction in a way that the AI can manipulate and reason with.
Okay, so let's bring this back to our original question. The cake that is intelligence and who gets to bake it. It sounds like we all agree that current deep learning models, while impressive, are not the whole cake. There may be an ingredient or a layer of frosting.
Yeah, I'll concede that. Deep learning is a powerful tool, but it's not a magic bullet. We need to combine it with other approaches to build truly intelligent machines. Maybe neuro-symbolic AI is the right direction. Or maybe something completely different that we haven't even thought of yet.
I think we need to go back to first principles and really understand what intelligence is. What are the fundamental building blocks that allow us to reason, learn, and adapt? I suspect the answer lies in a combination of symbolic representations, logical reasoning, and a deep understanding of the world.
And I think the key to that understanding lies in spatiotemporal reasoning. We need to build AI that can understand the world in a way that accounts for space and time, that can reason about cause and effect, and that can translate between different coordinate representations.
So, looking ahead, what specific research directions are you most excited about? Otto, what's next on your deep learning roadmap?
I'm really interested in exploring the efficiency of different activation functions and weight optimization strategies. We're building these massive models, but they're incredibly inefficient. We need to find ways to make them smaller, faster, and more energy efficient. Also, I want to dig deeper into how the self-play aspect of some models promotes the development of robust and generalizable strategies. Does it mimic human-level generalization?
I want to focus on developing more robust and expressive neuro-symbolic algorithms. How can we design systems that can explicitly represent and manipulate complex logical structures? How can we integrate these systems with deep learning to get the best of both worlds? I also want to explore the minimal set of rules and structures required to build intelligent systems independent of massive datasets.
I'm going to be exploring different geometries and how they're used in physics. Euclidean, Riemannian. Are there common underlying principles that we can use to model relationships within a spatiotemporal network architecture? And I want to understand if different representations can be organized into a network that accurately reflects the space-time fabric itself.
And I'm excited about merging the computational power of AI with a biological understanding of learning. How can we replicate or simulate neural mechanisms in AI models to enhance their learning capabilities? I want to explore how iterative self-play algorithms can be inspired by neural pathways in the brain. And can we integrate neuro-symbolic approaches with a deep learning framework to achieve a hybrid architecture?
That's a lot to unpack.
It's an entire career of research.
At least.
Absolutely. It's a huge challenge, but a fascinating one. The cake of intelligence is clearly a complex recipe, and we're all trying to figure out the best way to bake it. Thanks for joining us on this cognitive spiral. Until next time.